You also have another different example of parabolic motion. This one is if it was projected at a certain angle. Okay, this one is if it's projected at a certain angle. The example is in page
Yeah, this is the one you said that like usually question asked like this.
Yeah, you will normally see this kind of diagram inside your EJU questions, right? Right. So your question is actually based on this. Okay, now if you look at page 13 of your notes, now let's just consider the case where rather than we projecting an object horizontally from a cliff, we project an object at a certain angle from the ground. Let's just say that we project it with an initial velocity u at an angle of theta. Okay, so same thing as before. If we go and project the object like this, the path that the object will move would actually be a parabolic curve like this.
Yeah, it will eventually because of gravity, it will just
it will actually curve like this. Okay, so the same thing would also apply like what we did previously. We would actually say that you will still have constant velocity horizontally because last week I mentioned to you, if there's no air resistance here, horizontally there's no forces acting. So by right, it should just be moving with constant velocity according to Newton's third law, according to Newton's first law, or according to F net equals to ma, right? This one is the thing that I explained to you towards the end of the last lesson, because you asked me horizontally, there's no force. How does it relate to having constant velocity? Because I explained to you, it relates to Newton's first law. It also relates to F net equals to ma, where if F net equals to 0, A is 0, therefore constant velocity. And then for Newton's first law, I mentioned that Newton's first law was the one that said to you that an object remains at constant velocity or stationary unless a resultant force acts on it. Okay, so here same thing again. With air resistance being negligible, you still have constant velocity horizontally. So when it comes to constant velocity horizontally, you generally tend to use this equation where we say v is equals to s over t. But applied to this question, we would just say that ux equals to sx over t. Okay, where did your ux come from? Sx you probably can understand is your horizontal displacement. Now ux is your initial velocity, but in the x direction, in the horizontal direction. Now this part here is where you will start to use your resolution of vectors. You need to resolve your velocities, because you see in the first place your velocity is at a certain angle here like this. You can actually resolve it into two components, the horizontal and vertical component. You can actually resolve it into these two directions. So same thing as before, this portion which is adjacent to your angle would be u cos the theta. This one is actually your ux, your initial velocity horizontally. But then after that, this one, obviously, if you already identify which one is cos, the other one must be sine. This one must be u sine theta. This is your initial vertical velocity. Okay. The derivation, I mean the resolution is actually shown here. Okay. Described here. But I just kind of explain it in writing in a different screen here. Okay, so your constant horizontal velocity, the ux here refers to your initial horizontal velocity. Okay, that's how you got that. So your resulting expression in the end will just be sx equals to u cos theta times t. All right, but the thing here is that you just really need to recognize the general form of the equation, which was this one in the first place. Okay, after that you go and sub in the variables to match your question. All right, so if you move on to the vertical motion, same thing as before. the only force acting on your object is just the weight. There's no air resistance or whatsoever. Because you see, as your object was moving from here to here to here to here to here to here or to here, the only force acting is just the weight vertically. There's no air resistance to consider also. So your force acting is constant, your resultant force acting is constant, so your acceleration is constant, which in your case is actually equals to g lah, okay? So you can actually use your kinematics equation, which was mentioned to you. There are four, which is v equals to u plus at, s is equals to half u plus v times t, s is equals to ut plus half at squared, and then v squared equals to u squared plus 2as. Okay, so you're just applying it over here, where you just go and sub in your equations accordingly. So notice that here you see all those writings with u there, with subscript u. It's actually just meant to denote to you that you're talking about the vertical components. You're talking about the vertical component of displacement, the vertical component of velocities, and so on and so forth. All right. Now, different from the previous example, your uy here that you see is not going to be 0. Instead, uy, the initial vertical velocity, is u sine theta, which is actually this one over here. Okay? Because if you see the previous example in the previous page, we actually had something similar here, but here I mentioned to you uy is 0. That's the reason why it's 0 is because you're projecting it horizontally in the first place. At the start, right over here, your uy was 0. It's only after your object started moving that your vertical velocity start to increase. Okay. But now when you're looking at this new situation, your object was projected at a certain angle. Your vertical velocity is actually not going to be 0 in the first place. It has some value there. Okay. So you cannot just simply say that uy is 0 here. Uy is actually some value, which in your case is u sine theta. Okay. So after that, all you just do is you sub in the values accordingly. No? Okay. And another thing I should probably mention to you here is this. Your acceleration, when you substitute in, will be a negative. Because you see, when the object was moving upwards like this, being projected upwards like this one is your starting point. If you try to look at it horizontally and vertically, you are actually moving vertically upwards first and then horizontally rightwards. So this one will be your positive sign convention. Upwards is considered to be your positive sign convention here. Okay, which is actually indicated here. Now, your gravitational acceleration or your acceleration is directed downwards, right? So you compare this with your sign convention, it's going to give you negative. That's why here you see in your equations, when you sub in the g for A, you end up having a negative. It's because it is opposite to your sign convention in the first place. Okay? Right?
Okay. Because my G is opposite of my sign convention.
Yes. I mean, I can just try and clear this. I mean, I can just give you a simple example here. This one I mentioned is sy equals to uyt plus half at squared, right? So if I sub in everything properly, I'm actually getting sy equals to u sine theta times t plus with half negative g t squared. That's why in the end I get u sine theta times t minus half gt squared.
Because my sign convention, the first projectile motion is upwards and towards the right. That's why my sign convention it's upwards positive.
Yes,
And then but the constant acceleration downwards is against my sign convention. That's why it's negative.
Yes,
That's why my
correct.
g is negative. Correct?
Yes, correct. That's the reason why it's like that. That's how you make sense of the conventions. Okay. So far so good.
Yeah.
Okay, then after that, this one should be okay. Then after that, I just try and do for you the last diagram here. Okay, now when you go and project something upwards like this, say this one is level ground, it's the same horizontal ground. You initially started projecting your object upwards, okay, and it was at a velocity v, okay. So as I mentioned to you, you can actually resolve your velocities into two components, the horizontal and vertical component. You can resolve it into the horizontal component. You can also resolve it into the vertical component, okay. So that's one thing you know. Now, you will understand that as your object moves, it moves in a parabolic curve like this, mainly because of the fact that it's actually trying to move in two different directions. It's moving horizontally as well as vertically. Okay, that's how I explained it to you last week. Now, what is of interest to you is how the velocity changes horizontally and vertically. Now, from the part where I told you that horizontally you will have constant velocity, the Vx that you're seeing right over here would actually be the same throughout. If I tell you that this one is 10 meter per second, everywhere else would be 10 meter a second. It never changes. Okay. Now, of interest to you is the point where you have maximum height. Okay. This one here. You can understand that as you project it outwards, it will go up and then eventually it will fall back down. So there will be one point which is considered to be your maximum height, which is right over here. Okay. So let's divide this point like this. Now, from here to here, your object will actually be slowing down vertically. Okay. And then from here to here, your object will actually be speeding up vertically. Okay, now why do I say so? Because you see, if you consider this portion here on the right, sorry, left, your motion is in general upwards, right?
Yep.
But your gravitational acceleration is downwards. So based on what I mentioned to you earlier, your acceleration is opposite to your motion. You will definitely slow down. But then you look at the right hand side here, after the point of maximum height, you are starting to move downwards. So your motion is considered downwards like this. But your acceleration is also same direction. So this one would mean that you will speed up. Okay, correct? So that's why you see here when I look at the velocity vertically for this part alone, my vertical velocity will actually start to reduce. You see, it's denoted by the arrow length. It could be like maybe I tell you that this one was 30 meter per second. It suddenly dropped to 20 meter per second, and then after that it dropped to 10 meter per second. And then finally reaching maximum height, this one will be vertical velocity equals to 0. Okay? Then when I go past the point of maximum height, because I'm speeding up, my velocity will start to increase again. It could be that maybe now this one is 20 meter, sorry, this one is 10 meter per second. This one is 20 meter per second. I'm talking about the vertical velocity. This one is 20 meter per second. And then this one here is going to be 30 meter per second. Okay?
Because it's the same direction as my motion. That's why it's speeding up.
Yes, because the acceleration is the same direction as your motion, you will actually be speeding up. But if it's opposite, then you will actually be slowing down. Okay? So kind of makes sense here. All right. So that's one thing here. And then after that, I should probably mention is this. Now, when you're talking about the motion of your object being projected at a certain angle, the motion is actually kind of symmetrical. What I mean by that is this. Let me just clear off everything. If you say that this one is 10 meter per second at the start, then at the end would also be 10 meter per second. And then you say that here the vertical velocity is 30 meter per second. Over here at the end, it's also going to be 30 meter per second. Okay, you see it's kind of symmetrical. But just that this one is in opposite direction. Okay, because at the start it's 30 meter per second upwards, now it's 30 meter per second downwards. All right. So now if I look at the resultant velocity, you see there's a resultant velocity here because of the vertical and horizontal velocities combined together. This one will actually be 10 square root of 10 square plus 30 square. 10 square plus 30 square root of that give me 31.2 meter per second. So if you have 31.2 meter per second going upwards like this, over here, you will also have 31.2 meter per second. Same magnitude. Just that it's in opposite direction. I mean, it's kind of like mirrored along your x-axis. Because you see right over here, I tell you that you have 32.1 meter per, sorry, why do I keep writing 32? You have 31.2 meter per second. This one is at the start. At the end, you have this, also 31.2 meter per second. It's just that the direction kind of looks like it has been mirrored along the x-axis. Okay? That's why here I can say that your speed is going to be identical. But the direction is just mirrored downwards. Same magnitude, just that the direction seems to be reflected. Okay? Alright. So that one is on this. This is the understanding there. Okay, then we can start doing some of the questions again. Alright. Since you've gone through the first two examples, this last example, probably we can go a lot faster to complete out the calculations. All right, so let's look at the example in page 16. Okay. So we mentioned that football is kicked on level ground at a velocity of 30 meters per second and the angle 30 degrees to the horizontal. Assuming air resistance is negligible, find out the time taken to reach maximum height. Okay, so this is what we have. Time taken to reach maximum height. Let me just write down your kinematics equation. Equation 1, V equals to U plus AE. Equation 2, S equals to half U plus VT. Equation 3, S equals to UT plus half AT squared. The equation 4 is V squared U squared plus 2AS. Okay. So now, time taken to reach maximum height. Your maximum height is right over here. Now, what is one of the things that you can see here? I mean, when you analyze any kind of projectile motion, any kind of motion that seems to be curved, the simplification you always do is that you either analyze it horizontally or vertically. So right now, when you're talking about maximum height, like this,
vertically.
you will actually try to you will actually try to analyze it vertically instead. So you'll be using the constant acceleration vertically case, which will mean that you're trying to use your kinematics. So just now I mentioned to you that your vertical velocity will be 0 at maximum height. Okay, so same thing like what we did last week. Usually when we want to apply the kinematics equation, we try to list out the variables that we know. Now, do we know the time? We do not know. This is the thing that we want to find. But we know the acceleration is 9.81 meter per second squared. Do we know the displacement, the height? This one we do not know, right? Okay.
Yeah.
How about our initial vertical velocity? Do we know the initial vertical velocity?
30 meters per second.
Okay. Because we're considering vertical motion, let me just write this. Because this one, we're considering vertical motion. We consider the initial velocity, yes, but we must consider the initial vertical velocity, right?
Which is 0.
Initial vertical velocity. This one is your initial velocity. U, right?
That means we must resolve the angle.
Yeah, this one is just the initial velocity, but it's neither horizontal nor vertical, right? So this one we need to resolve. This one resolve it horizontally. This one also resolve it vertically. So horizontally, we know that your velocity will be 30 cos
U.
30. This one is ux. Then the pink colored arrow is your initial vertical velocity. This one is uy equals to 30 sine 30. Okay, so we actually know our initial vertical velocity, which is 30 sine 30. Okay, now what about our final vertical velocity at maximum height? This one we know is actually 0. Okay, so now based on what we know, there are two unknowns. T is what we want to find, S is not what we want. So we go and eliminate it off from our kinematics.
The first one, V equals to U.
Yes,
Plus A.
we use the first one. Second, third, fourth, we do not use. Okay, all right, so that's one. Okay, then now we use V equals to U plus AT. Before we proceed, we need to first establish our sign convention. Because our object is initially moving upwards, upwards is our sign convention, so V is equals to U plus AT. Solving in the values, it will be 0 equals to 30 sine 30 plus with negative 9.81 times t. So this one will be 30 sine 30 divided by 9.81. Our t would actually be 1.53 seconds. This is our answer. Now, if you want to follow EJU style of doing things, this one will actually be this one will actually be 0 equals to 30 sine 30 minus GT. So T is sine 30 by right, we know is 0.5 lah. So this one will just be 15 divided by G. No? Okay. This one will be how EJU will probably want it. No? Okay. So this is one. Okay. Then after that, we want to find. Yep. No issues. Alright, then we move on to part B where we want to find out the maximum height. We are again still using the vertical motion because we want to find out the
vertical height.
Vertical height. So same thing as before, we can easily see, okay, we know T is 1.53 seconds now because we already did it in part A. We know G is 9.81 meter per second square. S is what we want to find. Uy is 30 sine 30. By is 0. So in our case here, this one is pretty straightforward already. There's only one unknown, which is S. So looking at the equations that we have, we just really need to find an equation which has an S inside, which means that we can use either
S equals to half U plus VO times T.
we can use this, we can use this as well as this, right? Just that we cannot use equation 1.
Yeah.
Right? We can use either one. Now, let's just say we use equation 2 lah, because this one seems to be the easier form to use. So upwards is still considered to be a positive sign convention. S is half U plus V times T. So S is, sorry, the U is our initial vertical velocity. This one will be 30 sine 30 plus 0 times with our T, which is 1.53. So eventually we're going to get 30 sine 30 times 1.53 times 0.5, giving us 11.5 meter. This is our maximum height. Okay, then doing the EJU style will be S equals.
So 30 sine 30 is like 50. Oh wait, 30 sine 30 is 0.5. So 15 times 1.53 times 0.5.
Yes, 30 times 0.5, which would then become 15.
15 again times half, which is 7.5 times 1.53.
Yeah, wait. This one plus 0 times T. Okay. This one, sine 30 is 0.5. This one again is another 0.5 lah.
So that means it's 7.5.
0.5 times 0.5 is 0.25.
So it's
okay lah. Yeah, correct.
Yeah.
30 times 0.5 is 15, right? Then times
15 times 0.5 is 7.5.
Yes, so it's 7.5 T lor. Okay, so this one will be EJU kind of answer lor. Alright. So you can actually repeat the same analysis for different equations like equation 3 and equation 4 lah. Alright, eventually you get, I mean, equation wise, you probably get different answers, but in terms of the numerical value, you should be getting the same answer.
And it should be the same.
Sorry?
It should be the same, right?
Yes, correct. In the end, you should get back 11.5 for equation 3 or equation 4. It won't matter. Okay, but you're trying to do it the EJU style, finding the final equation, you might end up different now. All right. Okay, but you will still be getting the same answer numerically if you sub in the values. All right. Okay, now then the next one would be find out the time taken to hit the ground. When your object was being projected upwards and then it fell all the way down, do you want to find out what is the total time taken? Okay, now this one can actually be done very easily. There's an easy and hard way to do this. I can actually just tell you the easy way. Now, you consider this now. When the object was being projected upwards, let me just draw something here first. When the object was projected upwards and it moved like this one here being the point of your maximum height, it's actually correct for you to say the time that it took for you to go from here to here
It's the same as the time you come from.
It's the same as the time that it took for you to go from here to here, right?
Yeah.
All right. So, do you know the time that it took for you to go from here to here? You know, right? Because you already found out the answer is
times 2.
right? 1.53, right? Correct?
Yeah.
So this one will also take another 1.53.
So
So
1.53 times 2.
your time taken will just be twice that time. No? So your time taken would just be 2 times of 1.53, giving you 3.06 seconds. Okay, that's one way of doing this. Now, there's also another more tedious way of doing this. In your case, you could actually, let me just give you the EJU answer. This one T would just be 2 times of 15 over G, so it's 30 over G. Okay, this is EJU one. Okay, now this one I go to another different way of solving the same thing. This one is using a kinematics equation. All right. Now, the one thing I just want to ask you is this. If you look at how the object move, you want to find out you want to find the time taken. Let me just write it here on the right. Time taken is what you want to find. You know what is G, you know what is UI. UI is 30 sine 30. Do you know what is VY? You actually also know. Because just now I told you this one, right? If this one is, let's say UI 30 sine 30, at this point here, when you hit the ground, your vertical velocity will also be 30 sine
but
30,
negative.
but negative, the opposite direction. Your V1 here is actually going to be negative 30 sine 30. Okay. Then your displacement, let's just say, do you know your displacement? You started off here and then you ended up here. What do you think your displacement would be? It will be 0, right? Alright. So now, in your case, you really just want to find t. You only have one unknown. You could have actually just used some of these equations here. Let me just wipe it off first.
You can just use the easiest one, V equals to U plus AT.
You can use the first one. You can use the second one. You can use the third one. You just cannot use the fourth one. Okay, you can use any one of those except the fourth one. But let's just say I use let's just say
our side convention upwards is still positive, so
sorry.
Our sign convention outwards is still positive, so yeah.
Yeah, our sign convention is still outwards positive, but now you see if I try to use the first equation, outwards is positive, V is equals to U plus AT. Our V in the first place is talking about the final vertical velocity. This one is negative 30 sine 30. Our U is 30 sine 30 itself. Our acceleration is negative 9.81. Then we get our T. Now, T here, you will see is actually 2 times of 30 sine 30 divided by 9.81. So 30 sine 30 times 2 divided by 9.81, you're going to get the answer as 3.06 seconds. It's going to be the same. Okay? So you see, there are two different ways to approach this. There's a simple way, and there's a somewhat more complicated way of doing the same thing. Right? So this one is time taken to hit the ground. Okay, the last thing that we probably want to do is the total horizontal distance move. Okay, so let me just go out a little so that I can wrap up certain things. Okay, the question here wants you to find out the total horizontal distance move. This one we can actually, what we want to do is that we want to analyze the motion horizontally. Okay, wait, let me just find out for you first. Can I just erase everything here? Okay, if you want to find out the total distance, horizontal distance move, the keyword is already here. We want the horizontal distance, so we want to consider the horizontal motion. So this one, we will actually just use the equation V is equals to S over T. Okay, this one is for the constant velocity case. We won't be using the kinematics equation. we will be using the equation just for constant velocity, which is just v equals to s over t. All right, so do we know our velocity v? This one must be the horizontal one. Now let me just erase this so that it's easier to see. For our case, this one, we are talking about the horizontal motion. This v must be our horizontal velocity, which we actually already found out earlier. It's actually, if you look at our diagram, our horizontal velocity is this one, 30 cos 30, right? And it will be the same throughout the motion, isn't it?
Yeah.
So we can just use 30 cos 30 here for the total distance travel. We can just use 30 cos 30 for the velocity. So this one is 30 cos 30. The distance is what we want to find. Now, what about the time taken? So just now, last week I mentioned to you, in terms of the motion of an object that follows a parallel motion, the time taken horizontally is always the same as the time taken vertically, right?
That is 3.06.
So it's just going to be 3.06 because you see here, if it took you, wait, let me just highlight it. If it took you 3.06 to move in a curve like this, it also takes you the same time to move horizontally. So it will also be 3.06 seconds. So in your case, S would just be 30 cos 30 times 3.06.
15 times 3.06.
Then you will get 79.5 meter. Okay. If you're talking about 30 cos 30 times 3.06, you're gonna get 30 cos 30 times 3.06, you're gonna get 79.5 meter. Okay, so this one is your total horizontal distance move. Now, if you want,
So basically, the most important part of this chapter is to know your kinematics formula and know your sign convention.
And know your vectors.
yes, they're all interrelated.
Mm.
Okay, because if let's say you don't know a bit about the sign convention, how vectors work, sometimes people will start getting confused. How come this situation you have a negative? How come that situation you do not have a negative? All right. So as I mentioned, there's certain rules here to follow. Okay. All right. Okay, so the next one is actually just graph drawing. Let me just sketch out the graph and then you can check the shape of the graph. All right. We went through the calculations for kinematics where we talk about projecting something up at a certain angle, and then after that you move in a parabolic motion like this. So we went through the calculation part already. What we are just left is drawing the graph part. So we went through an exercise on drawing this graph for a previous example. So you know the logic and understanding behind it. So you just look at the part for horizontal motion, which is on the right column here. Did you get the graph shapes correct? Because this one, acceleration is supposed to be 0 acceleration. The velocity should be constant velocity. And then after that, the displacement time graph, it was mainly because V
Is the third graph on the right?
Is the line on the black line or is it below?
It's on the black line itself. Because you see this one by right should be your 0, right? 0 acceleration means A is 0. Okay, it should be on the black line itself. Okay, so when you're talking about the displacement time graph, this one is value of V is equals to the gradient of your ST graph. Okay. So I can say that this one, wait, let me use a different color. This one is constant positive value. This one by right should be constant positive gradient. Okay, so this one is pretty straightforward. But on the left hand side, the one when you're talking about vertical motion, the ones for acceleration, this one you can actually straight away relate it as constant acceleration. Which is downwards opposite to your sign convention. Because remember last time I mentioned to you, your sign convention tells you which direction is positive. In general, it tends to follow your initial direction of motion. So because your object was projected upwards like this at a certain angle theta, you will actually consider upwards to be positive, rightwards to be positive. Okay, so in our case, that's the reason why my acceleration is negative. Okay, so when you look at the velocity acceleration time graph and you want to relate it to your velocity time graph, you again will need to relate to A is equals to the rate of change of velocity. So the value of your acceleration is equals to the gradient of your ST graph or your VT graph. So looking at the value of your graph right now for A acceleration time graph, your acceleration time graph here you can actually say is constant negative value. So by right, your gradient
Constant
must be
Negative gradient.
constant negative gradient. Okay. Constant.
Because my constant acceleration is negative already.
Yes, correct. Okay, now from here you can actually deduce a few things. All right. Specifically when you're talking about your velocity time graph. Now, this point here is where you start to, this point here where V is 0 is actually your maximum height. Okay, just to recap a little how the motion was like. That object was projected like this. And then after that, it went in a parabolic motion like this. Okay, so we know that your object went up. Eventually, it will reach a maximum height, which was here. Here would be where velocity is 0. I mean, the vertical velocity is 0 lah. Okay, so here on the graph, you want to see where it is actually on this point here where velocity is 0. So that will actually mean one thing, actually. This part here was where you were moving up. This part here is where you were moving down. The moving up part is where you have positive velocity. The moving down part was where you have negative velocity. Okay, so you see,
Even though like the graph is like negative, constant negative, it doesn't mean the object is slowing down, right? It's just that it's going the opposite direction.
oh, you see the acceleration is negative. It doesn't. Your question here is if the acceleration is negative, it doesn't necessarily mean it is slowing down, right? Yes,
Yeah,
that's
yeah.
correct. That is correct. Because you see, what you understood was that if you look at the diagram on the right hand side, this part here was where you were slowing down. This part here is where you
Speeding up.
speed up. Okay, now if I talk to you about the part where you're slowing down, you can actually kind of deduce whether something is speeding up or slowing down by looking at the velocity and acceleration. You see, in general, for this part here, I am actually moving upwards in general. I mean, if I just consider the vertical motion, okay, vertical motion, if I just consider the vertical motion, my object is actually having a velocity in this direction upwards as it moves to maximum height. But my
Sign convention
acceleration is opposite to it. That's why this one I can say is slowing down. Okay, that's why I can say this. Okay, so you see, because the sign convention was also considered to be upwards positive, you see. This one is considered to be positive V. This one will be considered as negative G, right? So you see right now, if I just draw your attention to this one, this line here, okay? You see this part here is where you had positive V, but this part here is where you have negative G. You see, positive V, negative G. This one already implies to you that both of them are in opposite direction. So obviously they will slow down. Okay. But then after that, when you look at the other section, which is this one here, I already know that my object is going to move downwards after the maximum height. But at the same time, my acceleration is also downwards. So this one I know I'm going to be speeding up. Now, but with respect to my sign convention now, because I already said that upwards is going to be positive, this one by right will be negative V for me. This one again still maintains at negative G. So you see now negative, negative, then the same sign. So I'm going to have a case where they are speeding up. Okay, so like in my case, if I look at this part, this one is negative G, this one is negative V, it actually implies to me they are both acting in the same direction. Okay, right? So that's why we tell you that negative negative acceleration does not necessarily mean you are slowing down. Okay, it is really just a indication of the direction with respect to your sign convention. That's all there is to it. Okay, so this one is okay. Yeah, another thing that I can then do from here is to elaborate on your area. Okay, let's just say for example, I talked to you about the area under your velocity diagram. You recall that I mentioned to you that distance or displacement is actually the area under your velocity time graph. Okay, so let's just say for EJU style question, they sometimes will probably give you a graph, a velocity time graph, and then ask you certain things like what is the total distance traveled, or what's the displacement or position of the object. So you look at the velocity time graph right now, I can say that this one is area A. Maybe I just look at it like this. This one is area A, and then this one is area B. So what does the specific areas here actually tell me? So I can actually say that area A is distance move up. Area B is actually distance move down. Okay. So this is the two things I can see. Now from here, you can actually then work out what is your total distance move as well as your displacement. From here, if let's just say your question is worded in such a way they ask you to find distance total, this one will just be area A plus B. But then if they ask you to find the displacement, it will probably be something like A minus B. Okay, so this one would be something that does can actually come out in your EJU because of the graphs that I've been seeing. Okay, so this is what you can see. All right, so this one is talking about the velocity time graph. Now, next we talk about your displacement time graph. Okay, so for your displacement time graph, this one should be pretty straightforward, where we tell you that velocity is rate of change of displacement, then the value of your velocity is equals to the gradient of your velocity time graph, the gradient of your displacement time graph. Okay, so now from here, you can actually start to look at the value of your velocity time graph. Value here refers to your y-axis value. So if I try to look at the y-axis value for this one I can actually say that the value is less and less positive. This one, the value is more and more negative. Okay, in terms of the value is more like me looking at the y-axis value. Okay, so here one portion is having less and less positive values, another part is having more and more negative values. So from here, you can actually start to see the relation with your graph. Okay, like this one, I think I better just draw that whole line right across so that it's easier to see. If I draw this whole line here, it will be easier to see. Okay, so now if you look at your gradient of your displacement time graph, this one you can clearly see that gradient is less and less positive. This one, the gradient is more and more negative. Okay, so that's how you will actually make sense of your graph here. All right.
Yeah.
Okay. Okay, so that one is all right. Okay, so this is basically kinematics motion. Okay, there are quite a number of questions inside that I noticed that deals with this. Now, all these questions you've done so far actually have an important assumption. That assumption is that they told you that there is no air resistance. You have negligible air resistance. All right. Okay. So what about the case where you have air resistance? This is actually the last part of kinematics, and then we can actually wrap up this chapter.